So let's finish up this test. Number 13, an open top box is made by cutting squares out of the corners of a sheet of cardboard that is 3 feet by 4 feet. So I'm going to make a sheet that looks like it's about 3 feet by 4 feet, and we're going to cut squares out of the corners. And if you do that, you can fold it here and there and there and there. Flip this up, fold this up, fold this up, and fold it and make it an open top box. What size of squares need to maximize the volume? Okay, so we don't know the size of the squares. We'd call these X on each side. And the volume of a box is length times width times height. Too many variables to find maximize, but we should be able to, using the picture, figure out what length, width, and height is going to be. So the length would be from here to here. Well, that's going to be 4 feet minus x on this side and minus x on that. So it's going to be 4 minus 2 x's. That's going to be the length. The width is going to be 3 minus an x and an x. So the width is going to be 3 minus 2x. And the height is the length with the width of this flap. It's going to be standing up. So it's x. Now this is the volume as a variable of just one, a function of just one variable, x. So if I could try using the product rule on 3 things, but that's a little messy. So let's just multiply this together. 4 times 3 is 12. 4 times that's minus 8x minus 6x plus 4x squared. All of that times x. So 12x minus 14x times x is x squared plus 4x to the third. And now I can find the volume's derivative, which is going to be 12 minus 28x plus 12x squared. 3 times 4 is 12. And we set the derivative equal to 0 to maximize. So I have, let's see, what goes into all these? I believe 4 would. So I'd have, if I'm setting it equal to 0, I could divide everything by 4. 3x squared minus 7x plus 3 equals 0. This would be times of 4, but I can divide both sides by 4 and be gone. So that's the 12x squared, that's the minus 28, and that's the 12. So I got to solve this for 0. Let's see. 3 times 3 would be 9, minus 1 would be 9. I don't think I factor, so I'm going to use the quadratic formula. X would equal positive 7 over 2a plus or minus square root of b squared minus 4 times a times c. So 3 times 3 is 9 times 4 is 36 divided by 2a. And so that 49 minus 36 is 13. So it's 7 divided by 6 plus or minus the square root of 13 divided by 6. And square root of 13 is a little bit more than 3. So 3 plus 7 would be 10. 6, that's more than, that's close to half, which really wouldn't make sense here because I can only do up to 1.5. So probably the answer is 7/6 minus square root of 13 over 6 would maximize what size square? So the square should be 7/6 minus 13/6 feet. Okay. Now this one. It is defined in differential from -6 to 6. This may not be possible. We'll see if it is. It has, so we got to have a continuous curve from -6 to 6. It has 2 points where the first derivative is equal to 0, one at 2, so the function f prime is equal to 0 at 2, and it's also equal to 0 at -2. So it has a slope of 0 at those two places. And it has an x-intercept of 0 minus 2, x-intercept, y-intercept of 0 minus 2. I misread that. And it has one x-intercept at 4. So it goes through that point, goes through that point. There may be other x-intercepts. Can't have more than one y-intercept and be a function. The second derivative is negative from -2 to 0. So in here, it's got to be concave down. It is positive from -6 to -2. So here it's concaved up. And 0 to 4, it's concaved up. And on 4 to and it is 0 on 4 to 6. So no curvature. Okay. Getting complicated here. The first derivative is positive on the interval from 2 to 6. 2 to 6. The first derivative is positive. There's no curvature, and it's positive. So no curvature. I made it straight, but it's just the second derivative is 0, so it's no curvature. And the first derivative is positive from 2 to 6. So it has to be going up. It bottoms out at 4, or no, at 2, the derivative is 0. So it's got to have a slope of 0, concave up and hit 4, and it has a bottom somehow, and it has to come back up here. It's curved up through there. So it has to go something like this, and then from 2 to 6, it's positive. And what was it? From 4 to 6, it's straight. So I'm just going to make it that steep. Positive curvature, 0 at 2. It goes through that y-intercept. And the first derivative is positive from here to here. Otherwise, it's negative or 0. So it has to be going downhill all the way from -6 to 2, or go to flat. Well, it's flat at -2, and it's concaved up, and then it's concave down, and then it's concaved up. So it could go something like this. And let's see. The curve has an absolute minimum that is also a local minimum. Well, that could be here. But the absolute maximum is not the local maximum. Well, there is no local maximum the way I drew this, but there is an absolute maximum over here the way I drew this. There is no local maximum. So something like this would fit, I think, most of the things I said. Let's check. It's no cusps from -6 to 6 and connected. Has 2 points where the first derivative is 0 at -2, at 2 and -2. It has a y-intercept of -2, has an x-intercept of 4. There could be others. I have one at -1 also. The second derivative is negative on the interval -2 to 0. It means it's curved down. And it's positive from -6 to -2, curved up. And from 0 to 4, it's curved up, positive second derivative. And at 4 to 6, it's 0. So there's no curvature. The first derivative is positive on the interval 2 to 6. So that means the first derivative is positive, means it's increasing. And otherwise it's negative or 0. The curve has an absolute minimum. It's also a local minimum. It has an absolute maximum. Actually has one absolute maximum the way I drew it. That's not a local one because it's at the end. And there's no local maximum. And there's no local maximum on it. So I think I've answered all the questions.